Thanks for coming today, everyone. Today I'm going to be talking about leveraging HTTP request smuggling for remote code execution. And kind of just some background on this project. I'm a member of the Praetorian Labs team, and one of our services we perform for customers is attack surface management. And basically our team was tasked with spending about 2 or 3 months looking at different appliances our customers had on the internet to see kind of what vulnerabilities we could find within those appliances. So we kind of started off by creating a list of different services we identified, and then prioritizing based on kind of the breadth of, are there like other large companies that are using these applications, and in looking at impact as well. Like if you have something like Qlik Sense, which is very similar to like a Tableau solution, to set it up and use it, it's often on the internet, and it's going to need internal network access to access, databases to create dashboards and stuff like that. So we wanted to focus on appliances that if you were able to compromise them, you would be able to pretty easily pivot into the internal network and get a fairly decent level of privileges if you're able to actually find a vulnerability there. And really our directive was focused a lot around remote code execution. So like an attack chain involving like cross-site scripting wouldn't have been acceptable because it's too much work to exploit. We kind of just wanted like a point and click tool that you could run, reliably exploit, and gain access to an environment very easily. And so overall, we found about 5 different vulnerabilities, but today I'm going to really only be talking about 2 of them that kind of fit into a common pattern that we identified related to request smuggling. And a lot of it's focused around these scenarios where you have like a front-end server, and then you have kind of different tech stacks running on the back end, and you're kind of like centralizing your authentication within that front-end component, and then the back-end components are then trusting those systems to actually perform the authentication. And so if you can kind of cause some sort of like confusion between a front-end and a back-end system, you could potentially bypass authentication. And so to get started with request smuggling, this is an excellent diagram from PortSwigger's Web Security Academy, and they have some very good labs and stuff I'd recommend checking out if you're not familiar with request smuggling. But like there's a lot of like areas where this can happen, but like this is like the classic example of what people would think of with request smuggling. I'm going to be talking today about some other scenarios that are kind of interesting as well. But like in the HTTP1 protocol, you can have different methods of specifying where an HTTP request begins and ends. One of them is content length, which is like a static length of data, like you just 43 bytes in the example here. And then transfer encoding with chunked encoding is another method where you're basically like sending a number and then an amount of data, and then kind of keep doing that over and over, and then you send like a 0 to actually end that block of data. And so you kind of run into this scenario where like what happens if you specify both of these values? Well, if you have a front-end server that routes on one, and then a back-end server that uses the other one, you could have a confusion if those links end up coming out to be different. And so that's like a classic example. And the classic example of request smuggling in general tends to involve like you have a static TCP connection between the front end and back end server, and requests coming in from multiple clients are sent over the same connection stream, and then responses are sent back. And if you can like send like 1.5 requests here, where then the next client who might be in another tenant or something would send a request, you could redirect where the request is going and use their session cookie to like access an endpoint or perform an action that as that other user. But when you have scenarios where you have a front-end server that's performing authentication, and it's using something like header-based authentication on the back-end side, and it's trusting that front-end server, whatever value it's specifying there, you can also run into scenarios where request smuggling doesn't just involve impacting other clients, but it could actually be like a full-on authentication bypass issue. So to start off with Qlik Sense Enterprise, it's very similar to Tableau. It has a similar install base, a lot of fairly large companies. I think one of the things I've noticed with both Tableau and Qlik Sense is that a lot of companies tend to put these appliances on the internet. I can really only speculate as to why. I'm sure it just makes it easier for them to share that data with other people. But the application is quite interesting because, when you're looking at vuln research, especially from the perspective that we were going for, there wasn't really much to attack because the default configuration just has a login page. There's a handful of endpoints you can hit and not very much of an attack surface. And so we kind of just started by looking at the application architecture and trying to understand a bit more about where the attack surface is at and where there might be interesting vulnerabilities. And so there's really only a handful of places to look, like looking at whatever endpoints were accessible and authenticated, looking at the authorization and authentication logic implemented in the proxy, and then we were very interested in how the proxy service was performing routing. And so Qlik Sense, when it performs, the application is kind of built like a microservices application, and you can run it on one or more systems. So you could run, from my understanding, individual components of these services on dedicated servers, or you could run them all on one system. And so the proxy service will use a mutually authenticated TLS connection to authenticate with the backend services, and those backend services implement different components of the application. And so one of the things that we were really interested in was how this proxy service works, and if there's any because it's doing this kind of offloading of the authentication of the front-end server, if there's weird ways you can exploit path canonicalization, or the way the boundaries between HTTP requests are put together, there could be some interesting exploitation scenarios that we could identify there as well. And when we were looking at the proxy service code, I guess I should mention that the proxy service was a custom solution written in .NET. Typically, you won't see custom solutions here. In a lot of applications, they're using things like Apache, which I'll be talking about in the F5 example later. But one of the pieces of code that really stuck out to us is this forward post data function, where they're basically routing requests with post data, and they're looking at for the content length header, and then they're forwarding based on the content length header. And then if they don't find that, they're forwarding based on the transfer encoding header. And so this immediately kind of stood out as an example of a classical request smuggling issue, because the HTTP specification, when they actually say how do you handle both of these headers, they typically recommend that you look at for the transfer encoding header first, and then you forward based on the content length. You forward based on the transfer encoding header, and you need to drop the content length header from the actual request. And they were doing neither of these things. They were actually forwarding based on the content length and preserving both of these headers as well. And so one of the things we noticed is they also had this variable called blacklisted proxy headers, where they're actually looking at certain headers in an incoming request and removing them. And we ended up basically figuring out that this Qlik user account header was being used for authentication purposes. So in our test environment, we set up an attacker user to simulate an unprivileged user, and try to see what endpoints you could hit from that perspective, and kind of more out of curiosity than anything. And so they had this Qlik user header that was being sent on requests being routed to the proxy, and then we ended up figuring out that backend services were using this header for authentication purposes and actually trusting that header. And so we started mapping out the application, just hitting all the routes and kind of debugging it, and then instrumenting the code to see where certain request paths were being routed to, what internal service was being hit based on the path being used in the URL. So this isn't a full list of all the services they have, but some of the main ones are this repository service, which implements things like the management console and a lot of the core application logic. It also has a resource directory it uses to serve font files. There's a broker service, and that broker service, depending on the API prefix path used, will actually route to other components. And then there's an authentication service where you can either authenticate using built-in Windows NTLM authentication and forms-based authentication. The NTLM endpoint is interesting because you can hit that endpoint to see if you can read the NTLM challenge response message returned on authenticated to see, if you're looking at a target to see if it would be interesting, you can see what domain it's joined to, and if it's domain joined, another thing that's quite interesting from a targeting perspective. And so we started kind of looking at the backend services, because it looked like this was a potentially kind of dangerous scenario, where if you could trigger some sort of request smuggling issue, you would be able to specify your own Qlik user header and authenticate as any user account. But when we looked at the broker service, we kind of needed this precondition. Whatever is being used needs to use the transfer encoding header and ignore the content length header. And when we looked at the broker service, Node.js implementation itself would actually just return a 400 if you specified both of these headers, which I believe is also an acceptable way of handling this scenario. So you kind of had this precondition of you needed a backend service that would actually forward based on use the header, and it needed to ignore the content length header. So we had to give up on that service, but we did take a look at the repository service. This service was also written in .NET and used Microsoft IAS. And in this case, it would actually accept both of these headers in the same message, and it would process the request based on the transfer encoding header. And so ultimately here we were able to trigger a request smuggling issue. We noticed with IAS, if you specified like a body with a GET request, which the proxy service would support forwarding bodies of requests that you wouldn't normally expect to have a body, which is another kind of small difference in their implementation versus the actual HTTP RFC. But so here we're basically hitting a post handler and sending our smuggled request here. So basically the proxy service, when it forwards the request, would see everything in the red box here as being like one request, whereas the back stuff, the transfer encoding header would see this as two separate requests, with the second request being the request in the blue box here. And this would basically add a new administrative user onto the system. And we noticed that sometimes the proxy service would make calls to a service, and then it would use a repository account. And so we were able to impersonate kind of a privileged internal service account within the application, which then allowed us to actually perform administrative actions. The problem, though, is at this point we're only able to get it to trigger when we triggered a post request handler. Go back to this a little bit later, we were actually able to trigger this in another way. But for now, we thought, okay, this is great, but it's not necessarily what we wanted, because we wanted a pre-authentication remote code execution, and this would be something that you would be able to use if you were post-authenticated to get administrative access at this point. But we also kind of we didn't really want to add a new administrative user, we wanted remote code execution. Fortunately, here you're able to just invoke an endpoint in the admin interface, so instead of doing request smuggling to add a new administrative user, it ended up being pretty straightforward to just run arbitrary shell commands through the API, which is nice. There's some exploit chains you see where once they get admin, they have to do a lot of crazy stuff to actually get remote code execution from like the admin perspective, but that wasn't the case here, so that made our lives easier. But we did find a way to get around authentication. Again, like we later figured out we didn't need to do anything this fancy to actually trigger the issue, and I'll talk about that in a bit. But basically the proxy service we figured out wouldn't perform path canonicalization when performing access checks. So if you just had a path prefix and suffix that matched a request for a font file, those requests were allowed through unauthenticated because it was needed to load the actual login page for the application. But then when that request would get forwarded to the backend, the IAS would perform path canonicalization and would actually route it to the appropriate REST endpoint. So that ultimately ended up giving us a exploit chain that we could use, where we basically made like a very simple utility that you could use to run arbitrary jobs in the application, and we just like ran a netcat listener to connect over a bind shell, which isn't the most operationally secure method. I wouldn't recommend doing that on a red team or anything, but it's sufficient for proving out the risk at least. But I think a big one of the few key points I want to make is you want to be careful about trusting fixes. Oftentimes it's very difficult to fix vulnerabilities properly. It can be it can be difficult to fix these issues, especially when they're as complex as they often are. It can be easy to overlook kind of other scenarios when you're fixing the issue. And so typically for vulnerabilities that are of a more serious nature, we wouldn't do this for like a lower or medium risk issue. We'd like to do some sort of patch diffing where, you're likely familiar with this, but you can like take an old version of a binary and a new version of a binary and look at what changes were made between those, and that can often allow you to identify what code was added or removed to fix a vulnerability. And in this case, it was rather easy for us to identify what issue patch diffing can be harder when someone says there's like an RCE, but they don't tell you what it is. But we knew what it was, so this like very much stood out as being a interesting relevant was this HTTP header validation class that was added. And ultimately what they did is they added a validate function where you would look at a request and see if both the transfer encoding and the content length headers were specified within the request. And then they would also do another check by calling this isValid transfer encoding function. And this fix was a little bit dangerous because we figured if we could get one of these 3 Boolean conditionals to return false, we could potentially trigger a scenario where like IAS on the back end would still think it was like a valid header or something, and we could get around that. So like one idea would be like, well, what if you remove the dash between transfer encoding, or you change it to an underscore? Would IAS still like be flexible and allow that through to actually like interpret that? And we didn't have any luck there. Unfortunately, we tried a lot of stuff with that, but so we decided to dig into this isValid transfer encoding function. And so basically what they're doing here is they're doing a string split based on the header value. The encoding header can have one or more values that are comma separated. So you could say like gzip comma chunked is like gzip compressed data that's then chunked using chunked transfer encoding. And so they're just basically iterating through all these values and checking if it's any of these is in the encoding types array, which just contains one value, which is chunked. And so we got curious here if there's any way we could like get IAS to interpret this as being chunked encoding without using this exact value. Like what if you just said chunk, or you put like X chunked or something like that. And we ended up finding a way around this, which is basically when they're doing the string splitting, they're not removing prepended white space, but then when IAS parses transfer encoding header values, it will remove prepended white space before actually looking at the values. So like if you did like comma tab chunked comma, that would result in them doing on the front end doing a string comparison between chunked and tab chunked, whereas on the back end it would do a split based on the comma separated values, and then it would remove prepended white space and then do the check. So that allowed us to bypass the isValid. It would basically conclude that it was not a valid transfer encoding header, and then it would allow the request through as normal, and that got us around authentication. Got us around that check and allowed us to reintroduce the request smuggling issue. But they did add another fix, which was basically when you're requesting a font file, it needs to be either a GET or a head request, and they're now performing path canonicalization. So when you try and do like the path traversal thing to hit another endpoint, it wouldn't work, and you also couldn't use post. And as I said before, for some reason with IES, we're having issues like even just connecting directly to the back end IES service and messing with it. Like if you had a transfer encoding header value and add like a GET request with a body, like IES would just ignore all of that and only process the first request. But we ended up figuring out that with head requests, you could actually do the same thing with a proxy service. It was kind of violating the RFC. And another way it was forwarding bodies of head requests, which head requests don't normally have bodies anyway, but IAS, if you sent this request here where you said a head request requesting a font file, that font file doesn't even have to exist. It can 404. It'll actually process the body of the head request on the IAS side and see it as two separate requests. So that ultimately allowed us to bypass the original fix for the Qlik Sense vulnerability. And here is just a more rough POC of adding a new administrative user to Qlik Sense using this issue. And then kind of moving on to F5, kind of after we'd seen this, the request smuggling issues with Qlik Sense, we were very curious if we could find a similar vulnerability in another application. And so we started taking a look at F5, and one of the things that we noticed immediately was it was running some fairly older tech stack. It was running CentOS 7, older Linux kernel, and there's kind of quite a few CVEs associated with some of the dependencies, even in the most recent version, which isn't uncommon with a lot of appliances. But there was one that really stood out to us, which was this mod proxy HAP request smuggling CVE within Apache. And of course, given that we just found some interesting stuff with Qlik Sense related to request smuggling, we thought it would be worth digging into the CVE to see what we could do with it. And on our initial research, we did find an advisory that F5 had previously published kind of talking about this vulnerability and how it impacted their appliances. But it's since been updated. The screenshot is after they updated it. But they'd previously kind of said something around like, it can be like a denial of service issue. And, here's like a manual workaround you can perform if you're concerned about it. But they didn't actually release a full-on security patch for this issue. And so like we had launched just the latest version of an F5 appliance setup, and it was, there wasn't a patch for this. They were still running the older version. And the other thing that we noticed from reviewing some of the previous research into F5 is, well, the older CVEs use this thing that Orange Sci found. This is from one of his presentations, where a Tomcat would, if you give it a directory name with .. // it will see this as a reference to a parent directory, whereas Apache will see this as a directory name. And so someone found a vulnerability in F5 where since F5 basically uses Apache as a front-end server with an Apache module that performs authentication, and their backend uses Tomcat, they were able to basically send a request where the Apache would, perform path localization, check what path was being accessed, and see it as an allowed path because of seeing the .. / as a directory name. But then when Tomcat would actually get this request on the back end, it would perform path localization and actually hit an endpoint you could hit endpoints in the management console using GET requests that would normally require authentication. And so we knew that this similar architecture was being used with an F5 where you have a front-end server that's being trusted by a back-end system. And if there's any of these types of discrepancies in how they process things like access paths on files or where requests begin and end, there would be kind of opportunities for a similar type of vulnerability here. And so we thought, even though F5 said they did their own analysis and kind of concluded it wasn't an issue, it's, important. We're doing research. We can't make assumptions on that actually being true. And typically with dependency-related issues, it's important to kind of, first understand the vulnerability and then understand a bit on what the preconditions are. And that's usually where you run into issues is the preconditions end up being so extreme that it's like there's only like 5 systems in the world where it would actually be useful or whatever. But in this case, we kind of just wanted to understand the vulnerability first, and there's an excellent write-up from someone on their blogs, richterz.me, where they actually were the original person that audited the Apache AJP module and found this particular issue. So it's rather complex. You have to kind of understand some aspects of the AJP protocol. So it's definitely a good secondary resource if you're interested in learning more beyond this presentation. So of course, we kind of just needed to first verify that the preconditions were met. Basically, we noticed that for the management console and the F5 appliance, they're using the AJP protocol for communication with their backend Tomcat server. If you haven't heard of AJP, it's kind of an interesting protocol because it's basically what happens is when you have like an HTTP request coming into Apache, it gets converted into this binary format called the AJP protocol. A Tomcat processes that AJP packet, replies with an AJP packet, or it's actually multiple in both cases, which I'll talk about in a bit. And then Apache will convert that back into an HTTP response. So it's kind of like a transport used instead of HTTP between Apache and Tomcat for communication. And so this is what it looks like in Wireshark, just the AJP protocol message. It typically has like a couple magic bytes at the beginning, a length, and a code and a method for a post request. The fields do differ depending on the type of packet, which I'll talk about in a little bit. But that's just an example of what it looks like. And then here's an example request flow where, like if you have a post request coming in, AJP will convert this into actually one request packet and one or more data packets. The reason this is because the maximum AJP packet size is typically less than the maximum post request size, so it could get chunked into multiple data packets. But typically, like if you have a post request coming in, it would first send the headers and the request URL and everything like that in one request called a forward request packet. And then there would be a separate data packet that actually sends the post request body. And then if the packet is large enough that it needs to be chunked into multiple data packets, the Tomcat server would then request each chunk it needs kind of by sending a get body chunk packet. And then when it's done processing the request, it would return HTTP headers in the body, and then it would body would also be chunked depending on the response size, and then an end response message saying this is the end of the response, and then Apache would then convert that into your standard expected HTTP post request response. And so the issue here, it kind of relies between, you have kind of three components in the system. You have Apache, you have the mod proxy AJP module, and then you have Tomcat that are all kind of interacting with each other. And you have a persistent TCP connection used between Apache and the backend Tomcat system. And these systems need to keep track of when a message begins and when a message ends. And Apache, when it sees a transfer encoding header with the value chunked, it would process this as just the value chunked, whereas the mod proxy AJP module, when it looks at the transfer encoding header value, it just looks for the value chunked on its own. And so if you have the value chunked, Apache is going to interpret this as chunked encoding, whereas the mod proxy AJP module is going to think that chunked encoding isn't being used, and it's going to immediately send the data packet associated with the request if one exists without waiting. And normally if transfer encoding chunked is used with AJP, it's going to wait to send the data packet until the server requests it. And so basically you can trigger this where if you send a post request with a body and you set a transfer encoding header of chunked, Apache will process this properly because it supports that. And the AJP Apache module will send the headers and then the body immediately without waiting. And then when Tomcat processes this, it's going to see that the request headers don't contain a content length, and it's going to think that this is a post request without a body. And so then this results in a type confusion type issue where the next packet that the AJP processor and Tomcat processes, it's going to think that this is not, it's going to expect this to be a data packet. What it's getting is a data packet, but what it thinks it's getting is a request packet. And this is an issue because in the AJP protocol, basically, it doesn't have very many fields, unlike the header section, but basically the magic bytes and the message length are going to be the same no matter what, but then for data packet, the fourth and fifth bytes are going to be the data field and the data length, whereas in a request packet, this is going to be the HTTP code and method, so like saying this is a post request. And so basically, if we send a post request that has a data length that is equal to the expected value of the code and method for a post request, we can basically smuggle a second request past the front-end Apache server and get the back-end Tomcat server to interpret that however we want it to. But we have some limitations which I'll talk to in a bit. But basically, to figure out what data length we needed, you can just look at, there's no official specification for HAP. It's all the documentation that exists for it is people reading code. But there was a good one from Tomcat that kind of explains different aspects. It's not entirely like complete, but it is useful for understanding a little bit. And so basically for the code value, we need a value 2. And for the method value, we need a value 4. So basically we need a data packet that has a length of exactly hex 204. And in order for us to kind of trigger this confusion. And when we looked at the management console code, we noticed that it would read something. So HAP kind of has a contract of attributes and headers. And one of the attributes in HAP is this remote user value, where like the front end can set a value saying this is the user that authenticated using the remote user attribute. And then the back end will look at that to say this is the user that authenticated. And since we can smuggle our own HAP request packet, we can control the remote user attribute within our own HAP message. And so it's kind of a variant on header-based authentication. They actually also use a header called remote role, where you can set this value to say like what role you are in. So like if we set remote user to the name of the built-in administrative user account and we set remote role to 0, then that would basically give us administrative privileges within the application. But we have some limitations. The first one is, of course, our request has to be exactly hex 204 bytes in length. If it's less than that, it doesn't matter because you can add padding. If it's longer, you don't really have a solution to that. And the second one is that we can only smuggle a header packet and not a data packet, so our post request can't have a body. So we're kind of restricted here on what we can do because we can't send a post request with a body, and the length is relatively small. And if you have spent time looking at F5, you'll notice that their requests are often quite large, much larger than 204 hex bytes. So we had to do some trial and error here, and ultimately what we figured out was one of the things you can find sometimes is that like if you take what would normally be data in the post body and you put it in the query string, some applications will actually process that if it's a post request in the same manner as if it was part of the body. We did still have to use a post instead of a get because the endpoint would only work with the post, but you can sometimes put query parameters in the request, and that would substitute. They would actually see that the same way as if you'd put it in the post body, so that allowed us to get around the limitation of being able to send a post request without a body. And then F5, like this is the original request before we minimized it a bit, but like the length of just the query string is like 76. We need to get it down to 204. And so like, but a lot of these parameters are actually null parameters. So they have the parameter name and an equal sign, but they're optional and they're just treated as null. And it turned out that if you just removed a lot of these, you could get the payload size down below that 20F threshold. And then there are some other small tweaks, like if you can set a header to get around their CSRF checks, so that way you don't need a valid CSRF token when you're hitting this endpoint. And so that ultimately allowed us to get around a lot of the limitations we ran into. We didn't actually need a post body, and we were able to get the request size down with some tweaking enough to where it would actually work. And then so we do have a proof of concept video here where we first just start trying to log into the management console. And of course, the user doesn't exist because we haven't run the exploit yet. We perform the HAP request smuggling to actually add a new administrative user. And then we're also, once we get the administrative user, we log in to the system, and then we hit an endpoint within F5 that lets you run arbitrary commands. And then we also just log into the management console. In this case, though, you might wonder, like, well, why don't you just use the request smuggling to hit the arbitrary command endpoint like you did previously? And this is part of the reason. The reason here is with F5, it uses kind of different tech stacks on the back end, and one of them's Tomcat, and one of them's, I think, like more like CGI binaries and stuff. And there's like a /management endpoint where you can actually hit an endpoint to run commands, but that isn't actually using the Tomcat component. So we can smuggle requests to the Tomcat component, and that component didn't have the endpoint. So for proof of concept purposes, it was just easier to add a new admin user and then run commands. But there's definitely, we could have spent some more research time here to try and like find a better way that's not adding a new admin to trigger this. But we felt it was sufficient for, we're just building a POC. We can report to the vendor. We're not trying to build the most like OPSEC safe exploit toolkit or anything. So for a conclusion, I kind of just wanted to talk about offensive and defensive considerations, because I think there's some interesting ones here. From an offensive perspective, I think, if you're doing VR, definitely don't overlook dependency-related vulnerabilities. They can be kind of annoying because there's often a lot of them, and they often have a lot of preconditions, so it can be a lot of work to understand them. But even in a fairly widely used appliance like F5, you can actually find some pretty serious vulnerabilities just looking at dependency-related issues, not even needing to find a new or novel attack vector. The second one is, request smuggling. A lot of the classic examples are targeting, other users of the application. But if you kind of have these scenarios where a front-end server is delegating, a back-end is delegating authentication to a front-end, request smuggling is often a lot more serious than just interfering with other clients of the application. And then you definitely want to be careful if you're doing VR of making sure you're not completely trusting the vendor fixes or analysis, because security issues can be complicated to fix, so sometimes they're not fixed properly. And so that can also be a useful area for VR of, even if you didn't find the vulnerability, just doing patch diffing of, hey, this RCE came out, maybe they didn't fix it properly. That can get interesting. Or looking at, don't trust the analysis either of, like, if someone says, oh, we're impacted by this dependency related issue, but it's not a big deal. Sometimes that analysis is wrong. And I don't think any of these scenarios it was the fault, like the vendor did something wrong. It's just, fixing security issues can be hard. And in the case of F5, that one CVE is probably in like a spreadsheet of 1,000 other CVEs that they're having to triage and stuff. So, it's understandable how, you could overlook this when a lot of these teams are as busy as they are. From a defensive perspective, I think leveraging HTTP2 for backend communication when possible is a good idea. HTTP1 can be prone to request smuggling, and Apache JServe protocol is this kind of very legacy protocol that's not really documented, and I don't really think it provides any advantages over something like HTTP2, so I would recommend avoiding it if you can. Of course, like in the case of Qlik Sense, I think building custom solutions for things like request route parsing and routing and stuff like they did with the proxy service, maybe it would have been better to use something like Apache or Nginx, where it wouldn't have been prone to those issues in the first place, because it's kind of already been more of a hardened implementation. And you definitely need, I think, the kind of trusted front end trusted by the back end systems can be a good design pattern, but you do have to be very careful when you're doing like checks based on this, because like if you have scenarios where like one system performs path canonical differently than the other one, or differences in the way that request boundaries are defined as, it can turn certain vulnerabilities that maybe wouldn't have been as bad, like request smuggling, into something that's a lot more serious. And so there were two people that assisted me with this project, Thomas Hendrickson and Michael Weber. So I wanted to make sure I mentioned them, because this was not a project done in isolation, and they were all equal contributors to this project. So I'm happy to answer any questions that anyone may have.
All right. Do we have any questions from the audiences? You can raise your hand. I will go charge you. Then thank you very much for this insightful talk. Please give him a big round of applause.